think we can start. Good morning, everyone. I'm happy to be here today, and together with Laurent, he will introduce himself in a second. I'm happy to present the interesting and challenging comparison and merge use cases based on EMF Compare, which go beyond the typical use cases. So I'll have to be rude and introduce myself first, because Laurent will then take over and start the talk. So my name is Philipp Langer. I work with EclipseSource, and I've been working with EMF Compare now since I think three or four years. And yeah, I'm looking forward to the talk, and hand over to my colleague Laurent.
Okay, so I'm Laurent Delaigue from Obeo, the company that's behind EMF Compare and Sirius, for example, well known in the modeling community, and I've been working with EMF Compare for a while now. I wouldn't like to count. I'm glad to be here today to talk to you about advanced use cases of EMF Compare in a bit challenging contexts. So it's a talk that's a bit different from some talks you may see, because not everything always goes perfectly right in actual projects, and it sometimes comes out that some things that you would have thought easy to do are more challenging than planned. So we'll talk about that in a second. But first, for those of you who wouldn't know, what is EMF Compare and what are we going to talk about? Well, when you work with models, quickly you use a tooling that allows you to edit these models easily. So graphical tooling, textual tooling, it doesn't matter, but you have tooling to do that. And very fast you arrive at a point where you need to compare different versions of your models and sometimes merge them. And when you're here, you realize quite immediately that you cannot do that working with the textual serialization of standard models, because they are serialized in an XML format, XMI, and that is extremely hard to compare and merge, because it's just impossible to understand from an end user's perspective. They are used to seeing nice diagrams, nice textual syntaxes, and so on, and suddenly they should compare textual representations with technical details that they don't care and don't know anything about. So that doesn't work. And the point is that you need a tooling to allow you to compare your models in a way that end users that manipulate the tooling to edit the models will understand when they compare and merge the models. And that's exactly what EMF Compare is for. EMF Compare is an extensible, generic model versioning framework with the additional positive value that it is open source and freely accessible and hosted in the Eclipse community, of course. So it allows you to semantically compare versions of models and merge these models, taking into account the semantics of your models. That's the basic will and point of EMF Compare. It uses a number of generic algorithms to achieve that, and it has a very large number of extensibility mechanisms to allow you plug additional specific behavior, because you well know that when you deal with models, very fast you tune your semantics, you tune your tooling to achieve what you want to achieve with your models, and these specific customizations need to also be taken into account when you compare these models. Okay, so one of the typical use cases that is allowed by EMF Compare is to achieve version control on modeling artifacts. So we are used to version control when we deal with code. It's quite easy because algorithms to perform comparison and merge of textual resources like code files work extremely well. EMF Compare allows you to achieve the same with models. So you will be able to compare versions in different branches of your models and merge these branches and achieve the workflow that you achieve with source code. Okay, just a few words about the general overall process of EMF Compare when building a comparison. It's not straightforward, but actually computing a comparison between models is something that is quite complex, and it involves a number of steps that I will describe. So the first step is the model resolution. This is not straightforward at all. When you have a model, it's generally split in a number of files, and basically a tool like Git or a textual comparison has no idea what files constitute the whole model that you want to compare. And the user interface in general allows you to work on files, so you can right-click on your files and ask to compare this file with another branch and so on. So how do you integrate that with the models, where you need to not only compare one file at a time, but actually compare the model that part of it is on this file, but other parts of this model is on other files and has dependencies to other files that also contains other kinds of models. The model resolving phase is here for that, and it's based on a generic algorithm by EMF Compare that is able to compute the set of all the files that constitute your logical model. That is, all the files that contain your model as a whole that can be used for comparing, being sure you won't lose any information. This has a lot of extensibility mechanism to allow you to plug specific ways to compute this logical model. That's the first phase. First, we want to know what we want to compare. When a user selects one file, actually they want to compare more than just one file. Then there is the match phase. You have several versions that you want to compare, at least two, sometimes three, because there is a common ancestor to the two versions you compare. And you need to match the elements in one version of the model with the elements in another version. One straightforward way to achieve that is to use XMI IDs when you compare XMI models, because if you have XMI IDs, you know that an ID uniquely identifies one object, and any object with this ID is the same in any resource. So you can use these IDs to match objects, and that's very fast and that's very efficient and robust. When you don't have such IDs, it's more complex and it's based on heuristics to compute similarities between model elements, and it's not straightforward to understand that. Actually, it's really a very complex matter to compute useful matches between models that don't use IDs, and I'll come back to that later. Once you have matched objects between your models, you then can compute differences, because you know what objects exist on one side and not on the other, what object has changed, what object has been deleted, and so on. So you can compute the differences, and with that you finally have a comparison, the comparison being a list of matches and a list of differences between these matches. Then, before you display that to the user, you need to make a few more computations for the comparison to be understandable by the user, because there are all the technical differences at the lowest level possible, and a user will not understand most of these differences. They need to be wrapped into something they can understand, something that is close to what they manipulate in the tooling. So this phase, where we compute equivalences, requirements, conflicts, is to support that and to add information regarding this difference implies this other difference, because you cannot merge one without merging the other. This set of difference must be displayed as only one difference to the user, because it corresponds to one operation they made in the tool, and so on and so forth. And finally, you have a refined comparison that you can display to the user. Okay, a lot of work. Okay, a brief demo, just to show you that happily for the end user, it doesn't have to be visible and that complex. So here I have a simple conference model, which is a UML model of a conference data model. I should have opened it before, sorry. As you can see, tooling sometimes is a bit heavy. I guess my laptop is a bit overwhelmed also, because I have several environments for the demos. Okay, so this is the model I have, a basic class diagram in UML with a conference that has talks, speakers, rooms, and the talk has a talk level and is in a room and has a speaker. Okay, I know that somebody else has worked on another branch of this model to introduce other changes, and I would like to merge that in that model. So first, what I can do is compare my branch with another branch where my colleague worked. So I will compare with the tracks branch. okay, it tells me that I have to go to the synchronized perspective because there are several files changed. And when I compare my files, so this is the computation of all those steps that I presented earlier, and this is the result displayed to the user, something that they're able to understand. So you can see the differences in a graphical way. You can navigate between differences, so you can see that on my branch I have added the level. I go to the next difference, I have moved the speaker. This is a coordinates change, so this means that I have moved this box somewhere else. I have moved this box, I have added this enumeration, I have moved these arrows, I have added this reference and this reference. Okay, and you can also see the semantic differences. So I have added a property level to my class toe, I have added an association, and so on. And on the other side, I have added a track class, and I've added this association and this association. So it's very clear for the user what has been done on the left by himself and what has been done on the remote side by another user. And since you can see here there are no conflicts between the two branches, this means that I can merge directly, which I will do immediately if I can find my mouse. Okay. So I just go back there and I ask to merge my project, team, merge. I want to merge with the tracks branch. You can see on the bottom the tracks branch has been initiated on the initial commit, and my master branch is forked from there too. So if I merge the two branches, the result is a successful merge. Okay, and you can see that my diagram is behind is updated. I now have the track class that is added, the references and so on. My merge commit is created. It contains the changes of the two branches, so that's perfect. Also, what's interesting is you can see the merge is automatic. That's certainly not the diagram that you want to have as a result of the merge, because some things are overlapping, like the reference over the enumeration, these two boxes. So what you can do now, which is exactly what you would do when you merge text source code and you see that the result is not quite what you would like, is just edit this and amend the commit here to make it what you want to actually use. Because the tool will not automatically lay out a diagram for you and so on. You have to do your work here. The responsibility of EMF Compare does not go that far. Okay, so that's the typical use case I was talking about earlier. Now back to the slides. I don't know where they are. Here. Okay. Beyond the typical use case, the first use case that we want to talk about today is comparing heterogeneous models, where you have both graphical syntaxes and textual syntaxes. Because the DSL approach allows users to define graphical syntaxes, textual syntaxes, form-based syntaxes, XML-based syntaxes, which is still very much used, and probably other kinds of syntaxes. And each syntax is well suited for one typical concern. You want to describe static organization structure with graphical syntaxes. You want to describe behavioral features rather with textual syntaxes. So it's generally a good idea to use the best syntax for your concern. But your whole model is then made of resources of different kinds, some of them describing graphical models, some of them be using a textual syntax. Why is that a problem when it comes to comparison? First, the model resolving is complex because EMF Compare knows how to compute this model logical model when dealing with the XMI resources. When dealing with textual resources, it has to delegate to Xtext, if you use Xtext, which is, well, what most people do for textual syntaxes. And then resolving links with Xtext by default uses the local index built by Xtext. So if you think about the use case before, you have a branch in Git, and you want to resolve the links of a file hosted in a branch in Git, you don't want to use the local index of Xtext to do that. You would have to index what's in the remote branch of Git to properly resolve the links in the remote resources. And that's really very complex to achieve, not supported by Xtext out of the box. So the default implementation of EMF Compare would do something that's wrong and needs to be fixed. So we've been working on that. The second difficulty, among many, the main difficulties, is about the matching. As I said earlier, when you have IDs, you are sure you will get a proper, robust matching. When you want to match Xtext files, seeing them as models, you don't have any unique IDs to identify objects. Sometimes you have a name, and sometimes you have just nothing, not even an attribute to help you match an element. So that comes as something that's really complex to resolve. So what we've done so far is that during 2017 and 18, we have worked on improving the logical model computation to support Xtext resources out of the box, getting rid of the problem of resolving only with the local Xtext resource. So technically we use that behind the hood, but it's not really important. We have made a number of successful experimentations in 2017 and 18, and this will be available starting with Photon +1. So September, I guess, something like that. We couldn't make it for Photon. And we are still working on how to match Xtext resources correctly. So we haven't found a generic solution because we don't think there is a generic solution actually. So the approach is to make EMF Compare as easy as possible to customize, to deal with the specifics of a graphical, of a textual syntax. And this is something we work on currently. We have several ideas, but if you have this kind of use case, please come and see us, and so that we can get at least your feedback and be sure we address the right problems from as many customers or users as possible. Also, we have a number of best practices to stick with if we want to use that. If you want more details about that, come and see me after the talk. I think I'm already a bit late, so I will go faster. But mind how you serialize your references between XMI resources and Xtext resources. You need to have a stable URI, and that's not always possible if your Xtext element cannot be uniquely identified by a URI. That's not a trivial issue. Also, if you can always use XMI IDs in your XMI resources, you will be sure that then you can match easily your XMI files. That's what Papyrus does for UML. That's what we do in Sirius also most of the time. That's also really something that can bring success for comparison. Just a quick demo of what we can achieve so far, and I will handle back to Philip. So, just a second before I show a comparison, I want to show you, I have here a model that is made of both a textual syntax to describe cultures. So you can describe the activities to perform to achieve some culture. It's an imaginary DSL that we've already shown at EclipseCon, so I will use that one. You can describe that to cultivate corn. You have to perform the sow activity, then the weed activity, then fertilization, then check, and then harvest, and so on for each culture. So that's a DSL that allows you to put constraints of this kind of activity and so on. It's a textual DSL, and then alongside that you have a graphical DSL. Did I click? Sorry, something went wrong here. The demo effect. So I have a graphical DSL that allows you to graphically attach such kinds of cultures to resources that you have. Resources being the fields that you have, how they are watered, the resources for cultivating, tractors, the people you have available to perform these activities, and so on. I will show you in a second what you obtain when you compare this kind of thing. You will see the editor. So right now you can once again ask to compare your file with another branch. So I will compare my branch with master, and if I ask okay, you get a comparison where you can see differences. So you can see that you have added a culture somewhere. I will just show you other differences here. This is the graphical syntax of the DSL. So you have assigned some fields to a daily resource, and you have assigned this resource to the cultivation of corn. I can just show that here. So you have assigned it to wheat actually, and you have another resource with these fields assigned to the cultivation of sorghum. Okay, so on the left side you have added this assignment of this resource to this field. You can see it graphically still, and you can see other differences that are in the textual resource. Here you can see here actually that I have made a conflict. On the left side I've added a reference to the activity check that you could see in the textual file before, and on the right side I have removed this activity check. So here you can see what's the point of the demo actually is you can see that the EMF Compare comparison model aware detects a conflict. If you switch to textual comparison, you actually see no conflict at all. If you would merge that with textual comparison, you would just remove the activity check and add this line that references the activity that has been removed, which makes no sense. So thanks to the actual semantic comparison allowed by EMF Compare, you're able to detect a conflict that is really a semantic conflict that would be unseen and only detected by post-merge activities like validation or manual check. So that's the point of using EMF Compare to support semantic comparison, because even though you use textual syntaxes, you're still able to detect semantic conflicts that would not be seen otherwise. Okay, just back to the slide as a conclusion. We still have a number of concerns we work on. From the UI perspective, I went very quickly, but you can see that it's not obvious when you work on a textual representation to display in EMF Compare the differences, because by default we don't display the textual representation of this file. We display a tree. That's basically what you see in the outline of the Xtext editor. And in this tree, there are not all the elements of the actual Xtext model, so we are not able to display everything in a manner that the user can understand. So for the moment, you have to switch between the textual representation and the tree representation to understand really the differences, and that makes it not easy for users to understand their changes. And we still have difficulties with correctly matching Xtext resources in some context, because it's very easy to make a textual DSL that's very hard to match properly, and so you get comparisons that are much more complex than you would want, and that makes it harder for the user to merge. So these are concerns that I have no solution for. Actually, we are working on that, and we need more input from as many users as possible to have as many use cases to test. And now I've been very late, so please, Philippe.
No problem, I will be quick.
Okay, so
Thanks, Laurent.
That's the moment where we switch screens. Will that work?
Hopefully.
Go in front of it.
Perfect. All right, so the next use case that I would like to present It concerns actually quite a common requirement when you are generating artifacts out of your model. So for instance, artifacts like source code, specs, or documentation. Because if you're generating artifacts from your model, of course you probably also want to know which specific model change impacts which specific part of your actual generated artifact. So for instance, when you change the model, you would like to see what actually is the impact on the source code that you generate out of the model. So there are two, in order to address these requirements, there are two main ingredients. So first of all, you of course need very fine-grained information on your model changes. So for instance, which model element has been changed, at which feature value this model element has been changed. And luckily, EMF Compare got you covered here in this regard, because the comparison model that Laurent showed how it is computed in the comparison phase provides you all this information. The second aspect that you, or the second artifact that you need, of course, is generation traceability. So generation traces allow you to identify or to reason about which part of the generated artifact resulted from which part of the model. And obviously, if you put those two things together, the comparison model and the generation traces, you can find out if a model element has been changed on that value, what is actually what are the impacted files in your source code that has been generated, and exactly on which character range this change impacted your code. So that's a pretty cool thing. For this demo, of course, you can, so in general, of course, you can visualize the impact of model changes on your generated code in various different ways. For this demo, we chose to integrate it directly in the EMF Compare UI by using the extensibility mechanisms that EMF Compare provides. So as you remember, up here you have basically the overview of the changes, and if you select one, you see the details of the selected change down here. And what we did is basically we replaced or add an additional viewer for showing the details to show you the actual impact on the change. So let me just go to a model. This is we don't need to understand what this model is actually about. I will just show you that this model actually is used to generate code here. I will now do a couple of changes. So for instance, here I change the duration of this task, of that task, whoop, if I hit it, and of that task. And to prove that we actually generate code, I will also just delete this one, to push the check WDT and the refill water task. And as soon as I hit save here, if the generator works, we see that these files now get generated. If I now start a comparison of this model against the head revision, what we see is, again, as before in Laurent's demo, that we switch into the synchronized view and that we exactly see two changes. I thought I made three, but maybe I missed one. And these are exactly the changes that I did before. And for each of those changes, I can now switch to the impact on code generation, on generated code viewer. And when I click on that, we see exactly which line and character range has been actually changed or has been impacted by the change that I applied in the model. So for instance, here in this change impacted this line. When I switch to the other, then a similar line in a different class has been changed because of that model change. So that's pretty useful if you want to find out what actually or why certain parts of your generated code have been changed because of model changes. Right. So the next I will be really quick because I only have, I think, 2 or 3 minutes left. The next use case goes even further than that by exploiting the valuable information from the comparison model. And in order to explain that, I will just briefly give you a context of the use case that we had. So in this organization, which is producing some sort of hardware components, they have a database which describe each of those hardware components and describe which actions these components can actually fulfill. And of course, now a systems engineer could use this information within a model to build a system out of these hardware components where this system calls these actions of the different components. So what we did is basically wrote an importer that can read this information, fuel it into a model, and now the systems engineer can work with those actions. Of course, from time to time it happens that the available actions in these hardware components are not sufficient in order to build a system. So what the systems engineer now does is he or she actually changes those actions or extends them. And obviously they are now available in the model, but they are not available in the database and maybe also not implemented for the hardware component. So what we did here, and here is where EMF Compare comes into play, we actually wrote the custom comparison mechanism that takes each of those components and compares it, or the usages of these components, and compares them to the database. Exports them in a JSON-based change description of each of those components, and these change descriptions will then be fueled into a web application that can be used by these people maintaining those hardware components to say, yes, I want this, or I accept this change for this hardware component or not. And if they accept it, then we would push this information back into the model and also automatically update the database about the hardware components. The reason why it is a separate, separate web application and not directly in the modeling tool is because these people maintaining the hardware components are actually not using the same modeling tool as the systems engineer, obviously, because they're only interested in one component. Of course, there are several similar use cases where you can exploit the information from the comparison model and, for instance, generate change logs, reports, migration scripts for model-related artifacts, because it's very easy to actually do that, since the comparison model itself is an EMF model, so you can use any JVM-based language like Java, Kotlin, or whatever, and even generate things out of it very easily based on Xtext and Sirius, for instance. So let me just quickly demo that. Of course, that's not the real system that I can show you, but it's something that reassembles this HTML-based export system. So I will just quickly go to the check out a branch. Here, a branch with several changes that we now want to compare. So now when the user compares this branch with the, not the head revision, but the master branch, with branch master, then we see that there have been a couple of changes applied. And now if the systems engineer want to ask for permission that these will be taken into account for the next version of the hardware components, he or she can just request a review, and what this will actually do is, there should be a CSS behind that. Anyway, it should look way cooler like that, but it seems that the CSS of my web server went down. What we actually do is extract the information into a JSON-based change description that then will be fed into this web application, and then this hardware component manager could go through these changes and say, yes, I want to accept those changes or not. And if he hits accept, then we actually generate a second change description. That's the one that I've shown here, which would then drive certain actions like automating the merge of the model and updating the database. All right, just a few seconds left, so I will be really quick with just mentioning a few new features that will show up in the release of EMF Compare with Photon. So there are actually a lot of cool things to look out for. First of all, we have composite merge operations where you can, for instance, for one part of your model, say, resolve all conflicts by prioritizing the left or the right version, which is, of course, way more efficient than going through each of those conflicts automatically. We also now have, we now also enabled to change merge decisions later on, so you can now accept a change, then reject the change, accept the change, and then go back to the first change and change your decision on whether to accept or reject this change, which of course is way more intuitive and easy to do. Of course, technically it's very hard because we have to maintain all these dependencies between diffs, but this is now been done. And also we introduced key bindings and better text compare and so on. Maybe I can show just in the few remaining seconds the text compare. 1 second. here. So I will just check out the branch Lisa and compare it with branch Bart, and since Lisa and Bart always fight, there is of course also conflicts in their respective branches, as you can see here, for instance. And what I mentioned before with the composite merge decisions, you can just click here and say resolve all contained conflicts by prioritizing all incoming changes. And when you do that, you see that this conflict has been automatically resolved with one click. You can also, with the key bindings, now way more efficiently jump from diff to diff without having to click the right button here. And one thing that is maybe also interesting is the better text compare. So as you can see here, we now actually show the right text file, the serialization of the model that lies behind the changed model artifact, and actually also jump to the right line that has been actually changed based on a heuristic that works for XMI IDs. One really cool aspect of that, and that's the last thing, then I stop, I promise, is that we even show the virtual serialization of that file. So let's say now I merge that with a key binding. So I just hit Alt left to accept this change. And now you see here the duration is now set to 20 because we accepted this change, but we haven't actually saved the editor yet. So this is just virtual. And when I undo that, we see that it's 10 again. And this can be enabled or disabled with that button. All right. That's basically it. I hope it was fast but still valuable to you. Thanks a lot. And of course, find us at the conference or ask any questions that you would be interested in about EMF Compare. Thank you.